Welcome to Vail Clinic. This is a quick episode I'm doing just to kind of bring Andy up to speed on the Ward-Smith model because he seems to be kind of missing one of the basic points of it. And I feel like it's kind of just a math barrier, and just want to take him through the math quickly so he can see it. So for anyone who's trying to or follow along with this, I just pointed out to Andy that in WKO4 webinars he's using the wrong form of the Ward-Smith model. He should have been using the integral version instead of the derivative. And he claims that he understands the premise, just disagrees with it. I tried to point out that the Ward-Smith model, like all the other major models that are kind of extended, have a equivalent of W prime or F or C, whatever you want to call it, effectively anaerobic capacity. And Andy thinks that I'm confused, so I figured I'd just go to the paper, bring Andy up to speed. Okay, Andy, so Ward-Smith model right here. That's the paper. First clue that Ward-Smith is thinking in terms of capacities is right in when he's defining his nomenclature. So E0 is what you're looking for. E0 is defined as the capacity of the anaerobic mechanisms. So capacity, that's your W prime, that's your R for C, however you want to define it, however you want to measure it. It's going to be a little different if you measure it differently, but it's the same concept. It's capacity of the anaerobic system. And in the Ward-Smith paper, it is a little more confusing because he does try to break it up into this alactic and glycolytic mechanisms, but later on I'll show you where all he does is just add these two together to get one anaerobic capacity, and so it is pretty straightforward that way. Now, to kind of just reinforce the point that you should be using the integral divided by time rather than the derivative, I just want to go down here to equation 16 where Ward-Smith sort of lays it out. So equation 16 is going to be the equation for the aerobic power. So the derivative version right here is pretty clear that what you have is your anaerobic or your aerobic power at any given time is given by this simple equation right here. So you have a maximum rate, which is this R, and the rate isn't immediately available. Instead, the rate ramps up based on this exponential equation right here. So what you can see at time 0, this part of the equation is basically going to equal 1. So this is 1 minus 1, 0. So your aerobic power at time 0 effectively is 0. As this t gets bigger, then this ramps up, and eventually this side of the equation goes down to 0. And so then what happens at very long times is P aerobic equals R, which is your maximum rate of the aerobic system, i.e. this is your critical power. So now the problem is in WKO4 webinars, you use this form of the equation, which is the form of the equation that's looking at instantaneous power rather than the integral. So Ward-Smith lays it out right here, which says, which upon integration yields the amount of energy contributed by the oxidative mechanism. So for the webinars, what you should have used is this part of the equation right here and divided this by time, because this is, when we're talking about the mean maximal power curve, it's not instantaneous power, it's a capacity divided by time. So it's an average power for any given duration. So with that kind of clearly established, let's jump down to the anaerobic part of the equation. And so as I was mentioning before, here's the part where he says that the capacity of the alactic mechanism, AE, plus the glycolytic mechanism, EG, equals the capacity of the anaerobic mechanism, E0, is given by this equation right here. So what you can see is that even though he breaks it down into the alactic and glycolytic mechanisms, really it's just this one anaerobic capacity that you're after right there. So moving on. Same thing like the aerobic, you want to use the integral version of the anaerobic side of the equation. And so that's given right here. This looks a little bit confusing because Ward-Smith uses gamma instead of tau, and gamma he defines it as inverse seconds. So really what you should want to do if you want to think in seconds is just turn this into seconds, move it up here, call it tau. Easy enough to be done. But anyways, what he's saying is that here, your capacity anaerobic system, it's not all instantaneously available. There's a rate limit. And it's pretty straightforward that that rate limit is defined by this exponential ramp here. So effectively at very small times, this gets very close to 0, and then at infinite times, this gets very close to 1. So effectively what this says is that at longer times, you have your whole capacity available. At shorter times, you have a very small fraction of it. Regardless of whether you want to look at time 0 or time infinity, you get the relationship here, where again, to make it simpler, move this up here, call it tau, use regular seconds instead of inverse seconds, and what you see is that your capacity of the anaerobic system is really equal to the Pmax of the anaerobic system times your tau. So substitute that in, do a little math, and what you can see is that Pmax times tau, like I've shown with the equations I've been messing around with, is your W prime, is your FRC. It's the same thing conceptually, and this is the form of the equation that you should have been using in WKO4 webinars. It's also the reason why you get more of a wiggle in your residuals than you should. So it's something that you probably want to go back and fix that part of your webinars so that people aren't misled by it. I hope that brings you up to speed on the Ward-Smith model. If you have any other questions, I'd be happy to make more tutorials for you. Just ask, and I hope you got something out of this. Until next time, cheers, bud.